All right. So here's the problem. You have a picture of an atom, and I forgot to note that the atom is supposed to represent the element hydrogen. The picture is not saying that hydrogen has 3 electrons on it. I'm just kind of showing you the 3 different spots the electron can be in, and you see little arrows going in between the highest electron going to the second level. You see that there's a little squiggly line, E equals HV right there. And then the electron going from the second ring to the first ring, I also have another little squiggly line, and that's HV equals E. Okay, so we'll talk about that in a little bit. And then you see all that little stuff there, and then I wrote all the equations and the constants that you need here. So the first question says, what does N represent? What are these N's called on that picture? They're all called quantum numbers. They are your quantum numbers. And basically, what did Niels Bohr use them for? I mean, he just gave each of the energy levels a number, right? The first energy level would be N equals 1, the second one is N equals 2, and the third one so on and so forth. That way we can say clearly the electrons are on the first ring or the second ring or the third ring. And we mentioned it a little bit, but he also calculated how far those rings were from the middle. He calculated the radius, the radii for each of those, but that's beyond what we're covering right now. All right, so that's the first question. So second question is, calculate the energy of an electron on N equals 1, and then do the same thing for 2, and the same thing for 3. What equation would I use to calculate the energy of a photon or an electron or anything like that? The very, very first one right here. You're going to use the E equals negative 2.178 times 10 to the minus 18th joules. And you're going to multiply that times Z squared divided by N squared. What does Z represent? Z is the atomic number. And we're talking about hydrogen, so what's the atomic number of hydrogen? 1. So your Z is going to be 1 for all of these calculations. And that's why we liked when Niels Bohr was looking at this. He used hydrogen as an example because it made things easy for the math, at least. And it's the simplest element, so that also makes things a little easy to understand. What does the N represent again? That's your quantum number. So if we're going to talk about the electron on the first ring, as it says here, your N will equal 1. If you're talking about the second ring, then N will be 2. If we're talking about the electron on the third ring, N will be 3. So for the first ring, we're just plugging and chugging here. So you will do E equals your constant here, which is negative 2.178 times 10 to the negative 18th power joules. And we're going to multiply that by Z squared over N squared. So for the first electron, so I'm talking about the first electron, I'm going to put a subscript of 1 on that, so we know that we're talking about E1 for the first ring. So what is going to be your Z that we're going to square here for E1? Your Z is 1 because we're talking about hydrogen. So you have 1 squared divided by N squared. What's the N if we're talking about the first ring? N is 1. So on the bottom you're going to have 1 squared. So what's 1 squared divided by 1 squared? 1 again. And so you do 1 times negative 2.178 times 10 to the minus 18. What do you get when you multiply any number times 1? The same exact number. So your E1 was easy. E1 is negative 2.178 times 10 to the negative 18th power joules. So this is the energy required of an electron to live on the first ring. If we're going to talk about the second ring, what is the only thing changing on the second ring now? The quantum number is changing. So everything else is the same, but now instead of having 1 squared here, if we're talking about the second ring, the N is going to be 2 now, so it's going to be 2 squared. So I'm going to go ahead and write the whole equation out just so you can see the math. Negative 2.178 times 10 to the negative 18th power joules. We're still talking about the same element. Z is 1, so you have 1 squared. Now we're talking about N equals 2, so you're going to have, instead of 1, you're going to have a 2 here, so you have 2 squared. What is 2 to the second power? 4. So this whole thing is going to be 1 divided by 4, right? What are we basically doing to this number here? Dividing by a fourth, or as otherwise called, just you're taking 25% of it off. Or you're dividing it by a fourth. You're cutting it in a fourth. So you take that number, you divide it by 4. What will the calculator actually tell you? Did anybody actually get that one? It's that number divided by 4, basically.
Negative 5.445 times 10 to the negative 19.
Negative 5.454?
445.
445. My apologies. 445 times 10 to the negative 19th power joules. We can confirm this because I actually got this out of the textbook. It's problem number like 45 or something like that. It's one of your problems from the homework, I believe. So the answer would be in the back of the textbook for that one. It's a blue problem. Negative 5.445 times 10 to the negative 19th power joules is the energy required to live on the second ring, assuming that that is right. Now, if we talk about the third ring, and I'm guessing Cecilia's going to try to confirm it. Oh, never mind. Do you see the problem in there? Like number 30 something. It's somewhere in there. Well, don't worry about it. It's okay. I'll just get that later. Now for E3 though, we'll assume that the actual number is correct because I'm not focusing too much on you putting stuff in the calculator versus us just knowing how to do the problem itself. That's what I want to focus on. E3. So if I'm going to be on the third ring, what are we changing in the equation now? The quantum number again. Instead of n equals 1 or 2, now what will the n be for the third ring? It is going to be 3. So you're going to have negative 2.178 times 10 to the negative 18th power joules. And now you're still talking about the same element, hydrogen. So the Z number is still 1. But now we're on the third ring, so you're going to have 3 squared. What's 3 to the second power? 9. So now you're taking that number and dividing it by 9. What do you get from that? Negative 2.42 times 10 to the minus 19th power joules. Are we all in agreement? All right, I'm also not worried about sig figs or anything like that. Sig figs is kind of unimportant right now. I want to focus on just getting the actual numbers. You still get it too? Okay. So here's a trick that I like to do. I don't want to have to keep typing the negative 2.178 times 10 to the negative 18 power. I don't want to keep typing that over and over. So here's a trick that you can do. Put the number in, negative 2.178 E 18, negative 18. So I type that number in. I'm going to push this number called store, S-T-O. You push that button store, so it shows you an arrow, I'm sorry. So you have the answer that we just had, and now we have an arrow. We're going to assign, what, is there like a concert going on for these things? Y'all hear that? It's like bloop, 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 and then we got bloop, 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 bloop. This is freaking me out a little bit. We're going to actually have this number stored into a variable. I'm going to store this into the variable x. So you have this button here that has variables x, t, theta, n, so on and so forth. I'm going to push that and make that answer become x. I push enter. So now anytime I push x, x is that number. So I don't have to type that long number anymore. I'm just going to push x for that number. That's a shortcut I like to use because I'm lazy. So I like to make things easy. All right. Has anybody else done that before? You use the store function? Yeah, like, man, why type that number over and over? Pi, place constant, put it as x. We have to keep typing it over and over. So for the first one, E is just the number. E is just that constant. For E equals 2, I'm sorry, for the second ring, the E is going to be that number times 1 squared, which is 1, divided by 2 squared. 2 times 2 is 4. So here's what you should have gotten. Negative 5.445 times 10 to the negative 19th power. So that was correct. Now for the third ring, same number, but now we're going to multiply by 1 squared over 3 squared. 3 times 3 is 9. So we're dividing by 9 now. We should have gotten a negative 2.42, which is what we already had. Very interesting. Oh. We'll have to adjust that later then. Have to edit that out the video. Quite possibly, it could be something else is going on. I mean, if you're in the first energy ring and you go to the second energy ring, obviously, if you're going to a new ring, you have to absorb some type of energy. If you're going to transition back to a lower ring, you have to release the energy. But here are the values for those rings. What's more important is what's happening when you go from one ring to the other, not so much as what the actual value is for that ring. But here are your 3, and those are correct. Now we go to the next question. How much energy will a photon carry as an electron transitions from n equals 2 to n equals 1? And then we have other transitions. So what we're saying here is, if you're going to go from a higher ring, like n equals 2, to the first ring, n equals 1, what must an electron do to go back from the excited state to a ground state? You have to release that energy. We gave the electron energy so that it could go from the first ring to the second ring. Think about the flame test lab. That was you heating up the chemical in the flame. Now we're going to let the electron go back to a lower level. So the energy you gave it, it will get rid of it. So you will see that energy show up as light. That's what we're calling a photon here. And so we want to know how much energy is being carried away for that electron to go back to where it came from. So to talk about energy transitions, we use this equation, delta E. The change in energy is going to be your final position minus your initial position. So where were you at the end of everything happening minus where were you at the beginning of everything happening? So for this question, let's consider going from N2 to N1. So we're going to go from the second ring to the first ring. Where are we starting if we're going from the second ring to the first ring? Where are we starting at? We're starting on the second ring. So E initial would be the energy of the second ring, because we're starting on the second ring. E final is where we're going to go. We're going from the second ring to the first ring. So the final position would be the first ring. So delta E is going to be E final, which we're saying E final is now E1, minus E initial, which is E2. So delta E then, going from the from the second ring to the first ring, you're just going to plug in what you got for E1 and plug in what you got for E2. E1 is negative 2.178 times 10 to the negative 18th power joules, minus E2, which E2 is negative 5.445 times 10 to the negative 19th power joules. And you need to be careful because you have a negative number minus another negative number. So we must be extra careful on how we plug this into the calculator. So I'm going to type that in here. Since I have the negative 2.178 labeled as a constant, I'm just going to type X. And then we're going to do X minus, and I'm going to use parentheses and type in that second number, negative 5.445. E, and the exponent was negative 19, so negative 19. And here's your first delta E. Delta E is negative 1.6335 times 10 to the negative 18th power. The way I would like for us to write this would be delta E for the second energy level and one energy level. So here's how I wrote it. I wrote delta E with a subscript 2, comma 1. That means I'm talking about going from the second level to the first level. Delta E 2, comma 1. That change in energy, as I got in the calculator, is negative 1.6. I'm just going to keep 3 decimal places, so I'm going to go 3.4 times 10 to the minus 18th power joules. This is the amount of energy the photon carries. It's a negative number. Why should the change in energy be negative if I'm going from the second level to the first level? What does it mean to have a negative delta E, as we talked about on yesterday? Energy was released. That's why it's negative. I lost something. My bank account is so negative right now, it's ridiculous. That means I have lost all my money. I have taken all the money out, so it's negative now. I lost it buying too much Pokeballs on Pokemon Go. Alright? So on here, my delta E is negative because we lost that energy. So the photon is the package that's carrying that energy away. Alright? That's the second to the first. So going from, that's the first one, from N2 to N1. So from N3 to N2, how do I do that? I'm sorry, from N3 to N2, if I said that incorrectly. Final minus initial. So if we're talking about going from the third ring to the second ring for delta E, what's the final position if we're going from the third ring to the second ring? Where's the final position? 2. So we must do E2 minus, and what was the initial? 3. So E3. Our E2 was negative, and I'll just put it all together on Movie Maker or something. So E2 was negative 5.445 times 10 to the minus 19th joules, minus E3, which our E3 was negative 2.42 times 10 to the negative 19th power joules. So we go ahead and plug that in the calculator. Parentheses, negative 5.445 times 10 to the negative 19th power, minus, parentheses, negative 2.42 times 10 to the negative 19th power, close parentheses, and here's your next delta E. This delta E, so running out of room, this delta E is negative 3 point, I'm just going to, I'll keep them all, 0.025, woo, I have nowhere to write, E negative 19 joules. Joules. What does that number mean for us? We got negative 3.025 times 10 to the minus 19. When we go from the third ring to the second ring, what's going on here now? We're losing energy again to jump, to be from the excited state in the third ring to go back to a more stable state on the second ring. We're not all the way home, but we at least went closer. To do that, we had to get rid of energy. And that's the amount of energy you had to lose. Here's a question. Going from the second ring to the first ring, or going from the third ring to the second ring, which time must you lose more energy? When was more energy lost? Going from the second ring to the first ring, or going from the third ring to the second ring? Which one lost more energy? How do you know we're losing more energy going from the third to the second ring? How What should I look for to figure that answer out?
Make sure they have the same exponent.
First of all, make sure they have the same exponent. You know, but if you just look at the exponents, we got one that has a minus 18, and then we have one that has a minus 19. Which number is smaller, being to the negative 18th power or being to the negative 19th power?
Negative 19.
Negative 19th power is smaller. So when do we lose more energy? Going from the second ring to the first ring. This number's bigger. This number's bigger. This number is smaller. So what I'm saying is when you go from the second ring to the first ring, it's a lot more energy you have to get rid of than going from the third ring to the second ring. Because this delta E is bigger than the other delta E. Gladys is making a face, a stank face.
No, I didn't see it.
Oh, okay, all right. All right, yeah. What's the reasoning for this? How do I know that going from the second ring to the first ring, you have to lose a lot more energy than going from the third ring to the second ring?
Wasn't it because of the spacing? Like there's a bigger gap between N1 and N2 and just between N2 and N3?
Whoa! That is not what I was talking about, but that is true. If you remember the picture from the textbook, in the textbook, it shows you a picture. It shows you, it doesn't have the rings drawn as circles. They drew them as straight lines, though. It's like this. Something like that, sure. Okay. The first ring, n equals 1, was like this. So here's the nucleus. Here's the nucleus area right here, right? The positive signs that we are attracted to. Here's n equals 1 that has a space. I'm sorry, that is so wrong. Let's do this. Sure. So in between here and here is the space from the first ring to the nucleus. Let's make it more dramatic. Yeah, I know. Here's the second ring. Notice the decreased spacing in between. There's a lot more space going from the first ring to the nucleus, going from the second ring to the first ring, and then it just keeps getting smaller and smaller and smaller in the picture. I did not draw this appropriately to scale. But what the point is that as you go further and further away, the spacing in between gets smaller and smaller and smaller. I wonder why. Why is it so much space from the first ring to the nucleus, and then from the second ring to the first ring, and then so on and so forth? If I am an electron, what type of charge do I have?
Negative.
I'm negative. What type of charge overall does the
Positive.
you would I do that? I say the answer in the question I'm asking. What type of charge does the nucleus have?
Positive.
A positive charge. So if I'm an electron, where do you think I might want to go? I might want to go to the nucleus, right? Because I'm negative and it's positive is looking mighty good. I think I want to be there. Okay? For the physics people, do you guys remember seeing an equation like this?
Yeah.
Yeah.
So, something like this?
I don't know what that Q is. That a Q?
Or was it over here?
I don't know what that is, but I know it's N1 and N2.
Yeah.
Something like this, okay. What was this all about?
No idea.
Well, what did the M stand for? What did the M stand for?
We did like the...
So you had an object and you had another. What you do, Janasia?
Isn't that where we did like the wheels to go like this?
Well, I wouldn't know. I went in that room with you.
Yeah, it was like a pulley or something.
You had a pulley. Okay, so you had masses. But what was the R?
I don't know.
Radius?
That is actually it.
Yes.
It was radius or distance. It was the distance between things. At some point, though, you guys should have talked about charges, though. You have things that have charges that are attracted to things. And on the bottom, you're dividing by distance. What we see is that if you have two things attracted to each other. Hey, how about this? Let's just think about the sun. And you have planets that go around the sun. All right? Boy, that is so weird, that sound. You have planets that's going around the sun. Why is this asteroid so far away not going around the sun?
Wait.
Say it again, Juve.
It's too far out.
What force would make the asteroid go around the sun? Gravity. But does the gravitational force of this sun, is it powerful throughout the entire universe? Is every single object in the universe going around the sun? Why is not everything going around the sun? It's not close enough. I'm sorry. I'm dramatic, huh? If you're not close to something, how can you be really attracted to it, though? That's with anything in life. Planets, people. If you're, yeah, I gotta be close enough to smell the food. If I can't see it or smell it, how am I gonna know that the food is there and how am I gonna want it? Okay. If there's somebody you like in the school, it's probably because you saw that person, or you were near that person, or you were able to meet that person. But if you never met that person and was never close to that person, how could you really get attracted to someone? The closer you are to things, that's often how we become attracted to that thing. And we can actually, in physics, you guys were supposed to see how the attraction changes the closer or further away you are from something. Here we are talking about electrons now. For an electron to really want to be next to that nucleus, should it be closer or further away? The closer you get, the closer I get to you. Y'all know that song? Y'all know I can sing, huh? Y'all know I can sing, huh? No, I didn't ask for no backup singers.
Smile. It's a smile.
Solo, not a duet. I ain't want no backup singers, okay?
But it's just smile.
No, it's true.
It's more you make me smile.
It depends on which verse you're talking about.
Smile.
That's the boy part. The boy says see, the girl says smile, actually. Over and over again. I try to help us. Anyway. Yeah. I got pious stuff. Beyonce, I taught her how to sing. Okay. And we getting a karaoke game, too, once I get paid tomorrow.
That's gonna be fun. I want
For the anime club.
it.
You have to come after. And Just Dance.
Yes.
Both of those.
Okay.
Anyway, back at this.
I'm coming to anime club for that.
Anime club close. Anyway, that you have to get closer to be attracted. You have to be closer to be attracted. What happens though if you get further away? So what do you think will happen to an electron if it goes toward the outer levels, further and further away from the nucleus? What do you think would the electron really still be as attracted if it goes to the outer areas?
No.
Maybe not. Does anybody recall from chemistry last year or the year before, what do you call an electron that's on the outermost area? Valence electrons. And when atoms start bonding, as we'll talk about soon, they're going to be swapping electrons. Which electrons are the ones they swap? The valence. Why would it be easy to swap a valence electron? How can I take your valence electron? Why?
Least attraction.
And why would that electron not have attraction to stay at home anymore?
Because of the distance.
Oh, God, I love science so much. And I know they're like, I don't know that stuff. I don't even know what valence is. We'll get there. But for those that had chemistry before, they know we talked about valence electrons. And the valence electrons, I'm either going to steal your electron, I'm going to give you one, or we're going to share one. But why can we do that? Because you have them on the outside. They're far away from the inside. It's not attracted that much anymore because it's too far away. It's like, well, I mean, I'm here, I like you, but you got me on the outside, so I don't know if I want to be with you anymore. I bet I'm going to go over here to this other atom. Its nucleus is looking kind of good. Okay? That's why we're able to steal electrons from each other. Because of that lack of attraction. Now, there's a lot of lines on the outside, a lot of energy levels possibly that electron could be in. The spacing is getting smaller and smaller the further you go out. It does not take a lot of energy to go between one to the other because there's not really that much attraction anyway out there. If there's not a lot of attraction out there, it's not going to take a lot of energy to move between those rings, okay? It's only when you get closer and closer that the distances are farther, but also the attraction. The attraction is higher. So it's going to take a whole lot more energy to move from one spot to another, okay? So now we're back. Good job, Ms. Harris. All right. So now, here we are, back here. Don't tell me it's time to go already. Oh, okay. It's getting me scared. All right. So now here we are. We just did the energy from the second to the first and from the third to the second. And now the final one said, what's the change in energy going from the third level all the way to the first level? So to calculate the change in energy going from the third level to the first level, we need to know where's the final spot in the initial spot. If I'm going from the third ring to the first ring, what's the final spot we're going to? The first ring, minus, and where were we starting at? The third ring. So you do your E1 minus E to the third, to the third power, your E3. So we just come over here and we just plug it in. Excuse me. But do I really have to do all of that? Don't I know what the difference is going from the second ring to the first ring? And going from the third ring to the second ring? What can I do? Add up those differences, probably, right? But we'll just do it the long way for those who don't see that. So going from the third ring all the way to the first ring, we got to do E1 minus E3. So E1, minus E3. E3 was negative 2.42. E to the negative 19th power. That is not what I was supposed to type, boy. That dyslexia. X minus negative 2.42 E negative 19. So here it is. If you're going to jump from the third ring back down to the first ring, this is the amount of energy you will have to release. It's negative. That means we are releasing energy. So that transition is negative 1.936 times 10 to the negative 18th power joules. And there you go. That's the amount of energy that is lost or given away when you go from the third ring down to the first ring. Are there any questions about this problem? And you see all that junk right here? Welcome to AP Chem. Are there any questions about that? Make sure that you're always labeling stuff. It's very important you label. If you weren't labeling E1, E2, and all that, you probably will get confused by the time you finish the problem. Next question. Calculate the wavelength for each photon of light in problem number 3. What are we talking about here? What do they mean, calculate the wavelength for each photon? Where are photons at in this problem? What are the photons? What is it? It's the energy from what, though? What is a photon? Where is it in this problem or in this picture? What are the photons we're talking about? Electrons? No. The electrons are these circles right here on the rings.
The energy of the ring?
Not the energy of the ring. That's just the energy of the ring is how much energy the electron must have in itself to be there. What happens when I go from a high level to a lower level? What must be done? You must release that energy. The photon is that energy. The photon is that energy. The photon is the energy moving away. It will move like a particle, meaning there's probably some mass to it, a size to it, a speed for it to move, but also we can calculate the frequency and the wavelength of that photon moving away as the electron goes down. It's kind of like this. Dragon Ball Z. You have Goku sitting there going, gathering all that energy, right? And then what is he going to do when he sucks up all that energy and he's fighting somebody? He's going to release it. And what is it that will be released when he does that?
His energy.
In the form of possibly a...
What they call? You gonna write it out? Gladys. Okay.
You got Goku right here. Let me draw stick figure Goku, Super Saiyan. There he is.
That's so realistic.
Yes. So after about 3 episodes, he'll finally absorb all his energy, right? Take me 3 episodes to build up this energy. You know, and then finally, in a quick 30 seconds, what will Goku do?
Release the energy.
Kamehameha! Gladys, because of you, I will have to bleep out this video. Thank you for ruining it. Goku is going to go, and then he's going to go, Kamehameha! And then he shoots out this ball of energy. The ball of energy, the Kamehameha, will hit somebody and knock them back, right?
Or make them pregnant.
Or do what? The Kamehameha will hit somebody and knock them back or kill them or disintegrate them, okay? It's going to act like something that has a body to it, a mass, a particle. But also we know that it is energy. This is what's going on here. The Kamehameha, that's a photon. Goku is the electron. The electron absorbs energy and it will release that energy in the form of a Kamehameha, which is a photon. The photon is the energy that's released. So if you know the energy of that, I want to know, can we get the wavelength? How would I get the wavelength of the photon from each of the energies being released? The second equation, energy equals H, which is Planck's constant, times nu, which is frequency, right? What of this equation do I know for each of the transitions? I know H, which is a constant, that's Planck's constant right here. And do we know the E's that are coming out of each transition? Do we know the energy? Yes, that's what we got in problem 3. So if we plug in those energies, we can get the frequency for each of those photons coming out. Let's look at the first transition. If we're going to, for the E going from the second ring to the first ring, we already calculated that was the negative 1.634 times 10 to the minus 18th power. So I can plug that in to this equation here. We're going to do it this way to make this a little faster. So your E going from the second ring to the first ring, that's going to be equal to Planck's constant times your frequency of that transition. So we're going to plug in the numbers we have. What was that number we got going from the second to the first ring? That was this number here. So you'll do, oh wait, I'm sorry. You guys said that you like it when we rearrange the equation first.
Yeah.
Right? So we'll do that. So that means the frequency going from the second ring to the first ring will be equal to what? What will the equation be when you rearrange it?
Energy over Planck.
Energy divided by Planck's constant. So then you just plug it in. That E going from 2 to 1 was negative 1.634 times 10 to the minus 18th joules, and you divide by Planck's constant, 6.626 times 10 to the minus 34th power joules seconds, and you will get your frequency for that transition. Was there anyone who had an answer for that before we even got to this point? So maybe one person, 2, a handful maybe, okay. So we're going to plug that into the calculator, negative 1.634 E, negative 18, divide by Planck's constant. Nah, screw that. I'm not typing Planck's constant in here over and over. Okay, so I'm just going to do the same thing again, but I already have X as a number. I can use a different variable. So I'm going to use, let's type in Planck's constant, 6.626 E negative 34. That's Planck's constant. I'm going to store that into H, because it's H. So there is H. Sorry. So now we're going to do negative 1.634 times 10 to the negative 18th power, divide by Planck's constant, H. And that's what you should get. Negative 2.46, or if you want to round it, negative 2.4, I'll go 7 times 10 to the positive 15th power hertz. That's your frequency. And then how would I get wavelength from that? Use the other equation. Boy, look at all this math. I don't know if we're in physics or chemistry or college right now. Okay. This looks pretty crazy. Or calculus. Pretty sure calculus is involved in here somewhere. Back in the day, we didn't have physics and chemistry and biology and all that was separated. It was just science. A lot of the physicists and scientists who helped us come up with this stuff, they didn't really say that they were just a physicist. They were a scientist. So they had to know about chemistry and physics and math and biology. All of these things were all blended together, kind of. Yeah. Now we kind of divide into separate areas. So here's the frequency for going from the second ring to the first ring. And so to turn that into wavelength, we'll call that wavelength for the second ring going to the first ring. Wavelength times frequency gives you the speed of light. So how would I solve for wavelength once again? How would I rearrange this just for wavelength? Speed of light divided by your frequency. Speed of light, which is a constant speed of light divided by your frequency. And you would do this for all of the problems because I'm running out of time and space. I'm only going to do the first one, but you could do the other ones. So going from the second ring to the first ring, speed of light is 3.00 times 10 to the 8th meters per second. And you divide by the frequency we just got, which was 2.47 times 10 to the 15th power hertz, which is inverse seconds. You plug that in the calculator. Speed of light, I'll just type it in, 3.00 e 8th power divided by our frequency, which was 2.47 times 10 to the positive 15th power. And so the wavelength, because I'm out of space, I'm just going to come down here with it. The wavelength that I got from the calculator is 1.21 times 10 to the negative 7th power. Since we're using our basic units here, this is meters. That was meters up here, meters per second. This is meters. So this is my wavelength. I wonder what type of light that is. All right. For the last question, and you would do that same process for the other transitions, but for time, I'm not going to do them all because they all do the same thing. Even though this looks very complicated and difficult because there's a lot of calculations, but once you do one, you repeat the same process for all of them. Okay. The last question I asked is energy absorbed or released as you go from the first ring to the third ring. Energy is absorbed. For the mathematical support, you would run your calculations. What type of number would you get that shows energy is absorbed? Positive. You would have a positive sign if you're going from the first ring to the third ring. So if you did the calculations and you got a positive number for your delta E, that means instead of losing energy, you must have sucked in some energy. Okay? And that will be your mathematical support. And you would have to just show your math and show that you got a positive sign for it. Okay?